Okay, hello. My name is Fabio Fioravanti. I'm presenting joint work with Emanuele de Angelis, Alberto Pettorossi, and Maurizio Proietti. The work is about satisfiability of Horn clauses. In particular, we focus on Horn clauses that contain multiple queries. I start with an overview of Horn clauses and their use in program verification, and then I'll discuss about the Horn clauses we consider. There are Horn clauses containing algebraic data types, ADTS, such as lists and trees. And in these clauses, we specify properties using catamorphisms that are total functions in the functional setting or functional predicates in on-clause settings with a well-defined recursion schemata. And we are interested in checking the satisfiability of these Horn clauses and that contain multiple queries, and because we want to exploit the interdependencies, the relationship among the different queries. And then I'll move on the part where I showed how we transform Horn clauses and while preserving their satisfiability. And when doing this, we use properties from the queries in order to guess potential inductive invariance. And I conclude with experimental evaluation. Constraint Horn clauses have the same syntax and semantics of constraint logic programs. And they are a clause. A constraint Horn clause is a universally quantified implication C of this form, where H implied by this conjunction, where C is where H is either an atom, in this case C is a definite clause, or false. In this case, C is called a query. AIs are atoms of the form P of T1, K. And C is a constraint over a constraint domain D, maybe booleans, integers, reals, and so on, or combination of these domains, including algebraic data types such as lists and trees. And the semantics is the usual list demodel semantics. And constraint Horn clauses have the same syntax and semantics of CLP, but are not intended for direct execution. Instead, they are used as an intermediate language for expressing semantics and properties of programs. And usually, what they use it in the following way: there's a translation of the program and of the property to Horn clauses, and then these clauses, we check the satisfiability of these clauses. If the clauses are satisfiable, then the property is valid. Otherwise, the property is invalid. So we have this if and only if. Let's start with an example about the sorting algorithm, Insertion Sort. A short note on syntax: we use prolog-like notation for algebraic data types, so we such as lists with square brackets, and we have constraints over linear integer arithmetic and booleans in the a la SMTlib, but with an infix notation. So we have this predicate in sort, for insertion sort, with 3 arguments, and this predicate holds if z is the ordered list of integers with respect less than or equal that we obtain by inserting every element of this list into the ordered list in the proper position of the ordered list X. So if you remember the insertion sort from textbooks, it operates usually on an array, but you have a sorted part and a yet to be sorted part. The sorted part is X's, and yet to be sorted is Y's, and Z's is the final array. In this case, is the final list. And so, if the list to be sorted, yet to be sorted, is empty, then we are done. Otherwise, we insert first y and then all the y's into x's by calling this predicate ordered int, which stands for ordered insertion, and which we see later depends on insertion sort itself. They're mutually recursive. And we also have the predicate ordered, saying that a list is ordered. We have 2 arguments. The first is a list. The second one is a Boolean that is true if and only if the list is actually ordered. And so, for instance, we can see that the empty list is ordered, and if the list is not empty, then let us see the body. We have first T B1F is a predicate that extracts the first element of T when T is non-empty. Okay, if it is empty, F has a fictitious value, and B1 is false. Otherwise, it's true. So B1 tells us whether the list is empty or not. If T is not empty, B1 is true, and F is its first element. Okay, and we also have ordered T B2. So B2 says whether the tail of the list is ordered or not. And we have this constraint that says the H and T is ordered if this implication holds. This implication says that whenever B1 holds, that is, T is not empty, then H, which is the first element of this list, must be less than or equal F, which is the first element of T. So the 2 consecutive elements must be one less than or equal the other. And B2 must also hold. Notice that if B1 does not hold, that is, T is empty, then B holds. The singleton list is ordered. Okay? You may ask why we use this somewhat intricated way of defining ordered, but this is functional to the transformation, because if we are able to cast some predicates into the catamorphism schemata, then we are able to guarantee termination of the transformation. And so we have these properties, and we have these predicates, and we are interested in proving a property of insertion sort, saying that if we have this ordered excess B1 and ordered ZS B2, then B1 implies B2. So if excess is ordered, then also Z's, this is the final list, must be ordered. This was the assumption that excess is an ordered list. And this property, this implication, can be written in query form by moving this constraint from the right hand side of the implication to the left hand side and negating it. And so we can write this query as follows. Okay. Now let's see quickly ordered insert, which holds if Z is the ordered list of integers that we obtain by inserting y and then every element of y's in the proper position of the ordered list that we obtain by concatenating xs1 and xs2. And we have this definition of ordered insert that itself calls insertion sort. This is somehow the translation of the outer, the inner loops of the insertion sort in traditional textbooks. And we have, of course, use append, and which is the usual definition, and SNOC, which is the opposite of cons, and so SNOC LX holds if append L and the list of containing the singleton with X, LX holds. And last is a definition which is similar to first. And we have queries for insertion sort. And the first query is the one we already seen. And we have also the queries for the other program predicates that we use, such as ordered insert, such as append, as SNOC. For instance, let's see, a simple one that for SNOC that says that if we have this property predicates ordered, last ordered over XS and the resulting list. So if the initial XS list is ordered and is not empty, B2 holds, then its last element L must be less than or equal X. Now in this case, B3, which is the Boolean associated with the ordering status of the output, must hold. Okay? So we define this in these ways. Well, now we have clauses that we are using for translating the program. We denote them by P, and the queries corresponding to properties. And the properties for the program are valid if and only if the clauses, the union of these two sets, P and Q, is satisfiable. It is the case that, unfortunately, state-of-the-art unclosed solvers, such as Darica and Spacer, and Z3 Spacer, have some difficulties improving satisfiability of clauses with algebraic data types. So there are some approaches for trying to overcome this limitation that are based on induction or abstraction, free automata, and functional synthesis. This one is a paper that was presented yesterday at VMCI by Grigori and others. We, instead of extending the solving algorithm, we adopt a transformational approach. That is, we transform uncloses into equisatisfiable uncloses, and the transformation is sound and complete. That is, so the original clauses are satisfiable if and only if the final ones are. The transformation always terminates when properties are specified by catamorphism, and we exploit the interdependencies among multiple queries in order to discover the constraints among variables of basic types, such as the integer Boolean. We see that this transformation actually improves the effectiveness of unclosed solvers. Now let's see catamorphisms. Intuitively, catamorphisms are programs and predicates that are total, functional, and defined by simple recursion schemata on ADTS. Let's start with an example. Let's see list first. We have a catamorphism H must have this structure. So if you have a base case, a clause for the base case, and the clause for the recursive case, and in the body we have a call to H itself, and a call to another predicate combine that uses H, R, and produces a value res. Combine one is a total functional predicate or a constraint with these properties. For instance, length, the predicate for computing the length of a list is a list catamorphism. As you can see, the recursive call H is done on the tail, T. It's not done on the list itself. So there is some decrease in the structure of the data structure of the list. Similarly, for trees, we have these schemata that we can find, for instance, in the predicate computing the size of a binary tree. We have here two recursive calls, one on the left subtree and one on the right subtree. And again, a predicate that is total and functional. In this case, is just a constraint which sums the size of the left and right subtrees and adds one. We actually, this is the original definition of catamorphism. We consider a generalized version of catamorphism where we add an extra parameter that allows us to, for instance, count the number of occurrences of a given element inside a list or inside a tree. And we also allow for extra function calls in the body of the clause, or the second clause of the predicate. For instance, we can express the ordered predicate in this way. So ordered is a catamorphism predicate. And for binary trees, by doing so, we are also able to express the binary search tree property. So we stating the so a binary tree is a binary search tree with all. the constraints. Now we have a property that is based on catamorphisms. There is a quantified implication of this form. We have a program predicate P, and then with an input and output, we have conjunctions of catamorphisms, and on the right-hand side, we have a constraint C that works on basic types, maybe such as integers and booleans, that are computed by these catamorphisms. Okay, then in query form, we have this. You already seen this property in query form. Let's see now the transformation. We define new predicates using one program predicate and catamorphism. Then we unfold program predicates and catamorphism. Then we applied query-based strengthening for incorporating information from other queries, and then we fold using the introduced definitions. The definitions are clauses defining new predicates that are automatically introduced, starting from the queries, and based on fixed point computation. This is another contribution of this paper. And note that in some cases, definitions contain catamorphisms that are not present in the original query for program predicate append. Then we unfold, that is, we perform one symbolic evaluation step on the program predicate, on the program predicates, and we unfold the catamorphism as long as they contain instantiated ADT arguments, and then we apply functionality in order to remove duplicates catamorphisms. Then, this is another part, we use the queries that we are considering for verification, and we use them for strengthening clauses by adding catamorphism atoms and constraints to their bodies. And in this way, we exploit the interdependencies among the queries. We consider let us consider this clause. In green, this clause that we have obtained by unfolding from the previous step. This is a query under verification, and in green you see the common parts, and in blue you see the parts that are in the query but are not in the clause obtained by unfolding. And what we do is we add these atoms, this catamorphism, and the negation of the constraint in the query in this clause. In this way, we guess potential inductive invariance. And at the end, we are left with the folding task, where we have some definitions, and we fold, that is, we check inductive invariance and replace an instance of the body of a definition by the corresponding end. So at the end, we have the final program that contains only new predicates that have been introduced by definition. For concluding the experimental evaluation, we start with these clauses representing programs and queries. We apply our transformation, and we transform the clauses which are equisatisfiable. Then we translate them to SMT-lib, and we use on-clause solvers, in this case Z3, with the timeouts, and we get either SAT or unsat or unknown corresponding to timeout. And we have considered 170 programs for concatenating permuting, reversing, and sorting lists of integers, and for inserting and deleting elements from binary search trees, and 470 queries that are defined by using catamorphisms for list length, tree size and height, for computing minimum and maximum element of a list of a tree, sortedness, and so on. And these are the experimental results. We have a total number of 170 problems. We compared with Spacer. Spacer is very good at proving unsatisfiability, and indeed it was able to prove unsatisfiability all programs but one, and but was not able to prove satisfiability. That's the point about the main problem is that when there are recursive data structure, the standard CHC solver try to compute a model of the different predicates independently and then merge. Here instead we try to combine them and find a model of the combined predicates. So we are able to prove all the SAT and SAT properties with an acceptable time of read, mostly due to the translation to intermediate assembly lib file. I can conclude with standard complete transformation that works well on close with ADTs. We separate the tasks of inductive reasoning done by the transformer from that of solving done by Z3, in this case, standard CHC solvers. As on future work, we would like to compare with other solvers on ADTs, such as those listed here, but there are some issues about different formats that these tools use that must be solved. We would also like to extend the applicability conditions of the method, which are we are able to verify quite a large number of problems, but there are still some limitations. In particular, we would like to find novel methods for introducing candidate lemmas, candidate invariants. Okay, that's all. Thank you.
Are there any questions?
So as far as I see, this framework works for a fixed set of ADTs, right? Like list or trees and so on, but not arbitrary user-defined ADTs.
So termination is guaranteed as long as you use ADTs specified in this using catamorphisms. Mm-hmm. So if you do not use these, so in this case, the method is specifically tailored to guarantee termination for properties that are specified using catamorphisms.
So that means if I want to prove something with some of my data types, I have to supply the catamorphism for.
Yes, for the properties. Yes, you specify policy using catamorphisms if you want to use this setting.
Okay. So so if you have something like other ADTs like rose trees and so on, this does not work for this.
Like, sorry?
Rose trees, so where you have arbitrary branching.
I don't know. We haven't tried with this kind of ADTs.
So I just want to know what are the limitations of this approach.
Well, the limitation, actually, in previous work, we were more flexible about the kind of ADTs you could use, but we were not able, in that case, we are not able to guarantee termination of the transformation. Of course, you can always stop at any point and still have an equisatisfiable set of clauses, but you're not able to close all the loops, so to say. No, you're not able to discover all the inductive invariants.
Other questions? Okay, let's speaker again.
Okay, thank you.
Thanks, speaker again.